Position time graphs are an excellent way to graphically represent motion of a person or an object. It becomes really important moving forward to understand how to create a position time graph. So in this video, I just want to quickly show you two examples and explain a little bit about hopefully an easier way to start generating these position time graphs. What a position time graph does is it actually gives you a graphical representation of the position of an object, where it is or where it will be, as a function of time. So as time goes on, what's happening to the object's position. So we take a look at the example we have here. We have Mary walked 3 meters away from her desk over a period of 2 seconds before stopping for 3 seconds. She then takes 1 second walking back to her desk. So what's important to realize here is to take a look at some of these variables. So first we need to think, with Mary, what's happening here? Where is she? Well, if we assume that her desk is where she's starting, then we can go ahead and assume that at her original position, at the original time, when time is 0, her position is 0 because she's still at her desk. 0. There we go. So when at time 0, no time has elapsed, she hasn't changed position in any way. But if we keep reading, she then walked 3 meters away from her desk over a period of 2 seconds. So our next point, either point on the graph or point in her motion would be at 2 seconds. 2 seconds have elapsed. And where is she? Well, after 2 seconds, she's 3 meters away. Then she stops for 3 seconds. This one can get a little bit tricky, but first we start at 0. 2 seconds had elapsed. Now she stops for 3 seconds. That doesn't mean she stops at 3 seconds. It means she stops for 3 seconds. So 3 seconds past our last point should give us 5 seconds. So we know she went from rest. 2 seconds later, she was 3 meters away. 5 seconds later, how far away was she? Well, the problem says that she stopped for 3 seconds, so she didn't move. So she should still be at 3 meters. If we take a look at the last piece of information, she then takes 1 second walking back to her desk. So she takes 1 additional second. We were at 5. Now, 6 seconds later, she is back at her desk, which we know is her starting point. So we know her final point should be back at 0. She's back at her desk. Now we just have to simply take our chart, our position time chart, and just graph these points. So first, at 0 time, she was at her desk, so she had not changed any position. So our first point should be 0, 0. 2 seconds later, she was 3 meters away. So 2 seconds later, she was 3 meters away. So we can put that point in. And we can go ahead and connect this line, because in this case, we assume she's traveling at a constant velocity. Now, at 5 seconds, she's still at 3 meters from her desk. So at 5 seconds, she's still at 3 meters. So if we place that point there, what we wind up with is a horizontal line for this section. And that makes sense, because as 3 seconds goes by, 1, 2, 3, as 3 seconds goes by, there's no change in her position. This line is completely horizontal, meaning she has not changed position. And last but not least, she took 1 second going back. So at 6 seconds after she started moving, she's back where she started. So we should have 6, 0. We can connect that as well. We assume constant velocity. And here you have the position time graph of Mary's movement. Started at her desk, started to walk away. Her position is increasing over a time of 2 seconds. Once she hits that point, she does not move for 3 seconds, so there's no change in position. Remember, position is on the Y. There's no change in the Y from 2 to 5 seconds. However, the last second of her motion, she's traveling back to her desk. So at 6 seconds, her total trip took 6 seconds. She winds up back where she started. If we take a look at example number 2, it says Jim is playing golf. His ball is 5 meters from the hole when he attempts to put it in. His putt travels straight but misses the hole and comes to rest 3 meters past it after rolling for a time of 4 seconds. So this one is a little bit different. The reference point that you start with can be wherever you like. I'm going to choose the hole. The object is to get the golf ball in the hole, so my reference point at 0 will be the hole itself. You could certainly make 0, 0 the point where he's starting, but sometimes I think it's a little bit easier if I make my reference point, in this case the hole, makes a little bit more sense in terms of golf, but there are more than one answer here as long as the shape is the same. So if I assume that this is 0, position of 0 is the hole where I want that ball to be, well, now I need to read and take a look. His ball is 5 meters from the hole. what I'm going to say is I'm going to assume, since I'm trying to go towards the hole, I'm going to assume I'm 5 meters behind the hole. So at 0 seconds, I'm actually at -5. That ball is -5. It's 5 meters behind where I want it to be. He then attempts to putt it, and it travels straight, but 4 seconds later, 1, 2, 3, 4, 4 seconds later, it is 3 meters away. So I will say after a time of 4 seconds, it's +3. The reason it's positive, 4 seconds later, it's actually traveled on the other side of the hole. So we take a look at this graph, you can actually go ahead and say that anything that's negative is behind the hole before I putt, and anything above or positive is if it's past the hole. Ideally, I put this right in and it never even gets into the positive, but Jim here kind of sucks at golf, so he misses, and it winds up in this range here. So we take a look, at 0 seconds, the ball is -5, it's 5 meters away. So at 0, I should have -5. So this is my first point, this is where we're starting. He then putts it, and 4 seconds later, 1, 2, 3, 4, 4 seconds later, it's gone past the hole, so it should go over the x-axis because it's past the hole, and winds up 3 meters past the hole. All right, if we assume constant velocity for this case, we should get something that looks like this, something around here. Okay, so as he putts, as time elapses, the ball is absolutely rolling towards the hole, but it actually misses and goes 3 meters past it. Afterwards, the ball comes to rest, it says. The ball comes to rest, so at this point, it should just continue indefinitely unless we get more information until he putts it again. It should continue in this direction because as more and more time is elapsing, he hasn't hit the ball again, so the position is not changing. It stays at 3 meters for the duration. So hopefully this helps a little bit. You just want to take a look at where the object or the person is over what time period. I find it very helpful if you make small tables like this. I find it's very easy to graph tables as opposed to trying graphing straight from the problem. So good luck, and I will see you in the next video.